I'm Bob, N2CBH, and I offered to do a little bit of a presentation on vector network analysis, vector network analyzers. This is something I use in my daily work at my business. I run a company called Broadcast Devices Incorporated, and we make, among other things, RF power meters. And we often have to sweep the directional couplers that we use in those power meters, and vector network analyzer is used to do that. So that's just one use, and I've got a few of those with me today that I can show. And so anyway, let's just get started with this. So what is VNA and how do they work? Well, a vector network analyzer, or VNA for short, is a device that generates a sinusoidal signal, so it's a signal generator, to a device under test. And that device under test can be a load like an antenna. It can be a through device, something like this, like a filter. For this type of measurement, you need to use a two-port device. There are two types, there's single port and dual port measurements that you can make. So what the analyzer does is it shows both the amplitude and phase relationship of the incident signal to that of the reflected signal. It's essentially that, or through a device on a second port. Now, a scalar network analyzer can only represent the amplitude of the signals and a ratio thereof. An example would be a VSWR bridge that measures the ratio of the forward to reflected signal, but it can't tell you anything about other than that, about the load. It can't tell you what's going on in terms of reactance and that kind of thing. That's why you need phase. So the VNA is able to do both. So now, for example, return loss, that's a scalar measurement of a reflection. So you're looking at the signal going out and then comparing it to what's coming back. While impedance is a vector reflection measurement. This is why a VSWR meter does not measure impedance. It can simply tell you how much of the energy is getting out into free space and how much of it's being reflected back to your transmitter. Now, VNA allows us to determine impedance because the complex number which represents the vector, remember the 50 plus J0 or minus J something or plus J something, that's the complex number. There's a real part, which is the resistive part, and then there's the imaginary part, which is the reactance. But it can do both. It can show both. And we do this, we represent these things as S parameters or scattering parameters. And that term comes from the optics industry, actually. If you look at the picture there on the left, we all know about glass. If you shine light on glass, if it's really good glass, most of the energy passes through the glass with minimal interaction, but we know that glass can, because of the dielectric effect of the glass, can affect the angle at which it departs, and some of that light can be reflected. So those three things, the incident, the transmitted, and the reflected signal, are what make up an S parameter or scattering parameter. Now, in a VNA, we can do this with a single port or dual port. Now, I'm showing on this one, this is showing a device under test, something like a filter, or it could be anything really that has an input and an output. That's a passive device. So there are, in this particular situation here, you have a number of S parameters. So this would be like what we would call an S21 measurement, where we are listening on 2 and transmitting on 1. But you can also have an S11 measurement, which is simply sending the signal on port 1 and then receiving it back on port 1. And I'm ahead of myself because here's the next slide. So the VNA, as I said, is a signal generator and receiver in one package. Generates and receives a signal either on the same port or one or the other port for analysis of an antenna, loads, filters, RF networks, that kind of thing. So this is a simple S1 measurement where you're just using S11 measurement. Rather, you're using a single port to transmit and listen at the same time. Now, think Rig Expert. How many people have a Rig Expert? Right? Okay, you guys have them. Single port VNA. You have a calibration procedure for the Rig Expert? Did they give you a load and?
Yeah, there was a
Okay, but they don't give you an external load and opening. Really? Okay. Well, I'm going to show you why that's important to have a good one. All right, so this is a 2-port setup. I guess my graphic got a little screwed up on that, but so S1 would be the signal departing the generator, going to the device under test, and then coming back on S2. So this is a 2-port measurement. So the little nano VNAs, my professional VNA here. This unit is made by a company called Copper Mountain, and they make all sorts of vector network analyzers. There are other companies that still make them. Agilent, which is the old HP, Roda and Schwarz make some really sophisticated ones. This one is a little one that you can take out in the field. Some of the larger ones are not field instruments, but this is revolutionary, by the way. This instrument here that you can put in a little briefcase and carry to a site is a relatively recent event within the last 15 or 20 years. Before that, vector network analyzers were probably twice the size and about 40 times the weight of this case. They were very large instruments, and they rarely got taken out into the field. So what was used back then, I'm going to take these keys off keep doing that. What was used before that, and I forgot to bring it with me, I was going to bring that, is a thing called an admittance bridge, which is a simple device. It's a 3-port bridge, and that was what was used for years before network analyzers became practical to use in the field. So what's inside? Now, I want to preface this slide to tell you that this is a very oversimplified pardon me, diagram of what's inside of a VNA. You have a signal source, a directional coupler, and I have a few directional couplers that I brought with me today. Here's one of them right here. Of course, the one that's in the VNA is much smaller than this because you're not dealing with high-powered signals, but this is a directional coupler that is made by a company actually in Putnam County, Whirlitone, and we do a lot of business with this company. So signal comes in here, goes out, well, actually, no, that's the load. So the signal goes in here, goes out that way, and then you have 2 ports. You have a forward port and a reflected port. So what happens is the signal departs, goes through the device, but then it's sampled by both of these ports. So what happens is the one that's closest to the signal generator is your reference that's fed to a receiver. So that's a replica of what is being sent down the line to the device under test. The reflected port is simply what comes back. So what happens is that reference signal is compared to what comes back, and then you can do your scalar measurement. You can do something like reflection loss, return loss, or because you have the phase information, you can also then determine what the actual impedance of the device under test is. And remember, this is a sweeping oscillator, so it's going to sweep a band of frequencies what you set. So for a filter, for example, you may be interested in the bandpass of the filter. This is a bandpass filter. I had a huge notch filter, and I just didn't feel like dragging that thing out. I had it in the lab yesterday, and I was messing with it a bit, and would have been nice to show that, but I just was too tired to carry the thing. It stands about this high. It's a VHF cavity. This is UHF, so very small. So that's basically what's inside. Nothing more than that. Well, I say nothing more than that. Conceptually, nothing more than this. But what goes on in here, there's a lot of electronics in here to make all of this happen. Local oscillators and mixers and all kinds of things that make the thing operate. But essentially, this is what happens inside of a VNA. Now, calibration. This is really basically getting rid of errors. Now, calibration of a VNA is done to calibrate or cal out the effects of interconnecting cables, adapters, etc., which can influence the measurement of the device under test. So remember, coaxial or open wire feeds have a linear phase relationship with distance and also contribute to overall loss. So this cable, these cables, by the way, are very expensive. I bought this with this analyzer, and these were made by the same company, and they are exactly, and I mean exactly the same length, and they're the same type of cable. Does anybody know why they're exactly the same length? Okay, they're the same. I'm sorry? Well, yes, partly true, but it's the phase shift of the cables. It's equal. Okay, the phase shift is a linear relationship. So in other words, there's so many degrees of phase shift per unit length, and it's wavelength dependent. You're absolutely right about that. So for a full wavelength, the phase rotates 360 degrees, right? Because it's traveling down the coax. Now, you can have different length cables, and sometimes in the field we have to do that. Sometimes you have to have very long cables to measure a filter that's sitting on the floor, a broadcast filter, for example. So what we're going to do is we're going to calibrate the instrument to eliminate the effects of the cable, because there are two effects. One is a phase shift, and the other is an amplitude loss, because there's always loss in a coaxial cable, right? So we want to make sure that what the instrument sees is just the device under test. So these cables would be included, and if you're doing anything with your Rig Expert, by the way, you really need to put, pardon me, the Rig Expert at the load. Otherwise, you need to calibrate it with the cable involved. Otherwise, you're really not getting the full picture of what's going on. Now, there are times when you do want to include the cable in the measurement because you may want to determine whether the cable is good or not. Okay, so there's two cases for that. All right, so there's three basic. Oh boy, I hope I remembered my. Oh, here it is. I'm going to take this out. They supply you with calibration kits, which are, again, very expensive. And here's why. Because these are made to a very, very high tolerance. This one has an open, a short, and a representative load for the characteristic impedance of the cable. So this is SMA, so it's 50 ohms. They do make, this is a 50 ohm instrument. Most of these nano VNAs are 50 ohms, but professionally they do make 75 ohm versions of these. So this is a 50 ohm calibration kit. Now it's got, in addition to those three things I just mentioned, there's also a through port on this. Now, what sets this aside and makes this very different is the fact that this is machined to a very, very, very high tolerance. So that if you look at the open here that I have on the screen, that's a perfect open, because the center conductor is perfectly in the center, and it's a perfectly round center conductor and a perfectly round outer conductor. You take your pair of diagonal cutters and cut a piece of RG8, right, or RG8X, that probably happens to the end, okay? So that's not so open. What happens to the impedance of the cable if you do that on the right? What happens to it? It changes, right? Because it's dependent on the distance between, right, the outer diameter of the inner and the inner diameter of the outer, and then the dielectric material that the cable is made out of. That's what determines the impedance. So if you can't determine what that outer diameter is, because it's now an ellipse instead of a circle, it's kind of hard to know what the impedance is. Same thing goes for a short. We want to make absolutely certain that you have the lowest ohmic value between the center conductor and the end of the cable that you can possibly have. And then, of course, the characteristic load wants to be exactly 50 ohms and have absolutely no reactance anywhere in life, which is probably being a little optimistic, but you'll see these are pretty good. So that's why when you use your Rig Expert, if there's a calibration procedure, you should use it, okay? Because that's what gives you accurate measurements. So a little bit about calculations here. So on a scalar calculation, we all remember from the rules and things that we had to learn for getting our ham tickets. Reflection coefficient is basically a voltage, and we deal in voltages, reflected divided by the incident. So reflection loss, which is what we will measure with the VNA, is then in decibels, is then 20 log of the reflection coefficient. So an example here is a V incident of 10 volts and a reflective of 1 volt. So that's a minus 20 dB reflection loss, which isn't terrible, but it's not great either. That's probably about a VSWR of about maybe 1.3, something like that. And then you could have another example here. We have an even better reflected, less reflected signal coming back. And now you have a minus 40 dB reflection loss. That's excellent. 30 dB is approximately 1.06 to 1 VSWR. So 40 is like 1.03, or That's what you want in the lab, because you don't want any influence of the test equipment or the cabling or any of that stuff hampering your measurement. You want to measure the device. That's what you're interested in doing. So now, I think I talked about this a little bit, but the forward S parameters are determined by measuring the magnitude and the phase of the incident reflected and transmitted signals when the output is terminated in a load that is precisely equal to the characteristic impedance of the test system. So in the case of a simple two-port network, an S11 is equivalent to the input complex reflection coefficient, that's a mouthful, coefficient or impedance of the device under test, while an S21 is the forward complex transmission coefficient. By placing the source at the output port of the device under test and terminating the input port in a perfect load, it's possible to measure the other two reverse S parameters. Parameter S22 is equivalent to the output complex reflection coefficient of the output impedance of the device under test, while S12 is reverse. And all it really means is you're swapping the cables on the analyzer. That's really basically what all that means, whatever's convenient for you. Now, I want to talk a little bit about Smith charts. The Smith chart was developed by a guy named Jones, now actually Dr. Philip Hager Smith of Princeton University back in the 1930s. He was a professor there, and he wanted to come up with a better way to graphically illustrate what goes on transmission lines and antennas and things like that. These were used heavily during World War II. There were two radiation laboratories that did most of the work on radar and antennas. One was at MIT, and the other one was at Harvard. Harvard did the antennas. MIT did the radar work. I happen to knew a guy, and I worked for him for a short period of time, who was actually part of that team at Harvard, the Harvard Rad Lab. His name was Robert Silliman. I think he was a ham. He's a silent key now, but he did a lot of work up there during World War II, help us win the war. And those Smith charts were used a lot. So basically what Dr. Smith came up with, and I don't mean the guy from Lost in Space, were a way to graphically show transmission line parameters and circuit impedance. You can use it for other things. You can, if you're designing a circuit, an RL circuit or a RC circuit, RLC circuit, you need to figure out component values. You can actually use a Smith chart to do that. I'm not going to cover that today. I'm just going to introduce the Smith chart. And the reason I'm doing that is because you can graphically show with a network analyzer what a Smith chart is showing you. It can show you what the load is looking like, for example. So this is a Smith chart. And the first time I'd ever seen one of these things, I thought to myself, if a headache had a look, this is it. But all it really is, I'm going to stand up and actually, I'm going to skip to the next slide and I'll come back to this one. And the reason is because that's a lot simpler. All this thing really is, Smith was brilliant. What he came up with is he said, he took basically a Cartesian plane, which is, an X and Y axis, and he said, let me bend it and let's make it with circles. And that's what he did. So there are three basic components to all Smith charts. Well, this type of a Smith chart. There are different types of Smith charts. This line across the center here, which would normally be the x-axis on a Cartesian plane, is the impedance line. And it goes from the left to the right. It starts at a short circuit. Okay, this is zero impedance. Here in the middle is your characteristic impedance, the perfect. So in the case of 50 ohms, that's represented by 50 ohms. And then over here is an infinite or open circuit. So that's your open. So now, do you see why this is important? This calibration kit is important because you can display this stuff, and the only way you can do that accurately is to make sure that there's no errors in your measurement. The error correction that's done on a vector network analyzer is great. There's a lot of things going on to minimize errors so that you're getting the most accurate measurements. Now, there are some other components to this. So we can display impedance on one of these things. Well, impedance has two components. It has resistance and it has reactance. So whatever is above this impedance line is a positive number. So positive reactance is what? Do we know what that is? Inductance, right? And negative reactance is capacitance. So the inductance can be plotted on these series of, these are actually circles, these what look like arcs, because if you complete the circle, it'll be outside outside the circle of the Smith chart itself. So these arcs, as they stretch out here, are various values of reactance. And then the circles are what are called constant resistance circles. And they represent the resistive component of the impedance. And they start over here where you have a little dot because that's an open circuit. Okay, so it's an infinite resistance. And they get actually larger as you get toward the short. The outer circle here defines a short circuit where RE is equal to 0. So now what you can do when you take your analyzer and you see that complex number that says your Z is equal to 53 ohms plus J12, well, first thing you've got to do on a Smith chart, this is what is called a normalized Smith chart. So remember I said on the impedance line, it starts at 0 and it goes to infinity and 1 in the middle. Well, that's why it's a normalized chart. You have to multiply your characteristic impedance by whatever integer you come up with here. So you figure out what your resistance is, and then you go and you find out. I'm going to go back to the, see if I can figure out how to do that. Go back to the other slide because it shows. Oh no. Oh, there we go. You see, there's a lot more graduations here. There are a lot more circles. So what you have to do is you have to find the one that's the closest to the impedance that you're after you've done the normalization. So in this case, you have to divide your 50 ohms, let's say, or your 53 ohms by 50, and that would come up with, let's do an easy one, 55 ohms. So that would be, what would that be? It would work out to be what, about 0.9, I think, right? Something like that. So you'd find that on the resistance circle, and then whatever your reactance is, you go around that resistance circle until you come up to the arc that is, these outer numbers here also correspond to normalized values of the reactance, and that's your point. Let's just point here and say that's it, okay? And so now we can do something with that. We can then score a line from here to here and figure out what we need to do to correct that. So the Smith chart can be used as a calculator. Now, I'm not going to go into that today. I could actually do a whole, whoops, I'll lose my antenna. I could do a whole presentation on Smith charts. If you want, someday I'll come back and I can do that. I'll have some slides that are presented where we can actually solve some problems. So that's one thing you can do with this, is you can fix a load, for example. You can figure out what component you need of the opposite reactance and resistance to get it to where you want it to be, as close to 50 ohms plus J0. The other thing you can do with a Smith chart is you can tune an antenna by stub tuning an antenna. Joe, have you ever done that?
Stub tuning?
Yeah. I've never in 45 years of being a ham, I've never done it either. But that's one of the things you can use a Smith chart for, is to determine, and this is for coax or open wire feed. You can do stub tuning with either. I've made stubs, coaxial stubs, to make notch filters out of them to get rid of an annoying, like back when the days when cable television used to have these signals that would, that would radiate out of the cable system right in the middle of the 2-meter band, and your scanner would stop on them, and it would be nice to notch those out. So you make a simple quarter wave open stub to do that. But what the Smith chart allows you to do is to determine where on the line that stub needs to be and the length of the stub, so that you can notch out or you can match the impedance. Now, stubs are pretty narrow band, so if you're going to operate on one frequency or a very narrow band of frequencies, a stub is a good way and an inexpensive way to match the line, and you don't need a tuner in the shack. But again, the Smith chart allows you to develop what is called a complex conjugate, which is just the fancy way of saying whatever you need to do to fix that equation to make it 50 ohms J0. Or as close as you can get it. All right, where are we going here? And, oh, well, I just show these circuit equations here, which are the gamma, which is your reflection coefficient. And these are normalized versions of it, that correspond to this chart. So why do we perform a calibration? Well, I kind of said this already, but I'm always getting ahead of myself. As the previous slide showed, the Smith chart can represent the extremes of impedance from a short to an open to a nominal impedance. The network analyzer needs to see a representation of those three characteristics in order to be able to accurately represent the impedance between the two extremes. So by introducing a perfect short circuit, open circuit, and characteristic resistive load, the calibration standards are those perfect or really, really good standards. And this is an SMA standard, and I have a couple of different N type. This was already open. This is an N standard. This is an N female standard, and the other one is an N male standard. There's also a barrel in here for your through measurement. Now I'm going to go through, do a calibration here. Now we're getting into the show and tell, which is the interesting stuff. So I think I mentioned this too before, but again, part of the calibration, in addition to the calibration standards, we need to include anything that's between the port or ports on the analyzer and the device under test. So that's your cables. Coaxial cables between the analyzers and the load have loss and phase shift. We want to cal out those different things. So the only thing the analyzer will be representing will be the load at that point. And I think that's it. That's the last of the slides. So let's do some show and tell. Somewhere here I have. Okay, so this is the screen for this analyzer. And I turned this analyzer on when we first got here, and you're actually supposed to, in this modern age of microelectronics and surface mount components, you have to let this thing warm up for about an hour before it actually is optimized for making measurements. I'm not going to worry about how long it's been on. But we are going to go through the calibration. And as a matter of fact, I think I'm going to turn this around because it'll be easier. So you can see this is port 1, port 2 on this device. So what we're going to do is we're going to go through and we're going to set our stimulus, which is the band of frequencies that we're going to operate on or have this thing measure. And I'm going to go through this and I'm going to change this. So we're going to do a basic calibration. So the first thing you want to do is put your low frequency in, and let's do this. Nope, didn't like that. Why not? Oh, that's because I had the shift key on. There we go, 1 megahertz. And we'll stop it at, I think I don't have anything more than about 500 megahertz here today, so let's do that. Now, the reason we want to do that is because it's going to calibrate within those two. So we're going to do a 499 megahertz bandwidth span here. Okay, and then once we get that done, well, the measurement we'll come back to. We want to perform the calibration. Okay, corrections turned off. Actually, we want to turn that on. Cal kit. We want to use we got to tell it which cal kit we're going to use. And where the heck is it? There it is. I want to use the 911T. I think that's what this one is. Yep, that's the one I want to use. Okay. And then the cal kit. And now we're going to do what's called a 2-port calibration. So we're going to do this twice. We're going to do it for each port. So now I'm going to take my N connector cable here and I'm going to attach it to port 1. We're going to do each port individually, and then we're going to do a through port. So we're going to start with the open. That's the button right underneath the one that's in blue there. And for this, I got to take my glasses off because I can't see anything up close with those on. So we'll start with the open circuit. And what we're doing is we're just telling the analyzer, hey, this is a perfect open. Okay, once we get that check mark, we're done with that. We can do the short. And again, if you got a rig expert or a nano VNA, you should be doing this every time you start the thing up and use it. Now with the nano VNAs, they give you a cal kit, and you know what? We're going to see how good they are. At least the load anyway. We'll see how good the loads are on those. All right, and then we got to do the load. This is this guy. Okay, now we'll do the other port, do a through, and then we can make some measurements. Okay, we're back to doing an open. Whoops, let's make sure that's tight. There are actually, I should be using those actually, there are actually torque wrenches that you use on N and SMA connectors to give you the proper amount of torque. Okay, that's the open. Sure.
You have to do it in that sequence, the open it first and then the short?
Yeah, you have to do it, well, on this instrument, yeah, you have to. Yeah, I don't, you know what, actually I don't think it makes any difference, but generally you just follow the, the sequence. As long as you're telling it what it is. In other words, you check the box for whatever it is. I actually don't think it does make any difference. I just, what happened here? Okay, I didn't hit the button. Okay, 50 ohm load. All right, now we're going to do the through, which is connecting the cables together through our perfect through port. We think it's perfect. Now note that these cables are SMA output, which is what I use most of the time in the shop there. But what I'm not going to be able to do is to include adapters in the calibration, which you really should do. The problem is I don't have a BNC cal kit, and I don't have a PL259 cal kit or SO239 cal kit, which you would need to do the things I want to do today. Okay, one port. We're going to use subclass 1, and we're going to apply, and we are done. And this is why you use the torque wrench, because these are a little unruly to get these off without a little bit of help. This is what torque wrench looks like. This is made by a company called Huber and Sooner, which also makes the connectors. All right, that's off. Okay, so now we can actually make some measurements here. So let's do this first. Let's go in, and we're going to do an S11 measurement, which means we're just going to use port 1. And I want to look at the return loss of this coupler. Oh, look what happened. So now, remember, we're scanning from 1 megahertz out to 499 megahertz, well, 500 megahertz here. And the return loss is about 25 dB. Now, if I take this load off of here, it's 0, right? Because we get a total reflection. So that's what the analyzer is showing you here, the reflection loss. Okay, now something else that, something's loose here. Now this coupler is designed to work from 80 megahertz to 1,000 megahertz, so it's really not fair. So let's go back to the stimulus and change it to 80 and 1,000, or otherwise known as 1 gigahertz. And now the picture gets a little better. because this is the area where we're going to use this thing. But it's still in the 20s in some places. All right, so now we can convert this analyzer to an S21 measurement where we're using both ports. Now, what we do very often in the shop is we want to know what the loss is. In other words, here's what a directional coupler does. You have your through port signal. So it wants to pass all of the signal through the device without any attenuation. Well, there's always a slight bit of attenuation. But ideally, it's passing all of the signal through. But what we're going to do is we're going to pick off a little bit of energy at a specified level that we can measure, and that's our sample port. So the one that's closest to the input side is going to measure the forward power. Now this one is set for 60 dB of coupling, which means that the signal going through here, let's say if it's a 1 kilowatt, that would be plus 60 dBm. What comes out of here is 1 milliwatt, or 0 dBm. Okay, that's 60 dB of loss. Same thing on this port, but what this port is looking at is if this is connected to an antenna, it's looking at whatever's coming back in this direction. Now, the isolation between these two ports is called directivity. That is the ability for the one port to ignore what's still going on at the other port. That's important, and we're going to measure that. We're going to show you how to do that. So I'm going to do that right now. So let's go in and let's go back and change this to an S21 measurement, and we're going to connect the input to port 1 or S1. And our reference line is in the middle. That's 0. That's where the yellow is. And then we're going to look at the forward port. Oh, I got to set my reference, the lower reference, down lower because you're not going to see it. Where do I got to do that? Let's move the reference up. We have 100 dB dynamic range here, by the way. In other words, it's plus 50 up at the top and minus 50 at the bottom. That's what this instrument is. Let's see. I don't know which direction we have to go here. Let's see if that works. Yeah. Okay. Let me do it one more so we can see what's going on here. I could move the reference all the way up to the top if I want to, but okay. So now you notice the yellow line that's flickering around down there at the bottom. That's the loss across that frequency spectrum. Okay, so from 80 megahertz all the way at the left, all the way over to the right. Notice how flat that is? That's equal loss. These couplers are manufactured. This is what is called a compensated coupler. Normally, a coupling loop, there's a capacitive effect. And if you don't cancel out that capacitive effect, what do you think would happen to the coupling as you go up in frequency? It would increase because capacitance, the capacitive reactance drops as you go up in frequency, right? So you'd have as a matter of fact, we use couplers like that are made that way with a specific purpose because the directivity is better on those than this type of coupler. But for power measurement, this is really handy to have. Now, you can't really see what's really going on here, but what we can do is we can save this trace, save the trace data, and let's do that. And we can turn this into, where are we putting this? I guess we can put it in here. Let's go here and let's, I thought I had a folder for VNA. Here we go, VNA data. There we go. Let's do it there. So we're going to call this one forward coupling. You can call it anything you want. I usually use the serial number and all that so we know which one it is, but for brevity, we'll just do that. And then we can go and look at the data in a spreadsheet. We can get rid of this guy at this point. And then we can open a Cal spreadsheet. And that's the one I just did. And there's the data, tabular form. So 80 megahertz, the actual loss is 60.141 dB, or it's out to a lot of decimal points there in the decimal places. And you'll notice that it's not precisely 60 everywhere. There's some ripple in it. You know, it drops to 59, 85, and so on and so forth. Now that's important to us when we make a power meter. We need to know exactly what the coupling loss is at a particular frequency. Because we don't know that, and we can't precisely measure what the power is. We need to have a resolution of about 0.05 dB. That's 1%. That would be a 1% error. So if you don't know what the resolution of that out to the second place after to the right of the decimal point with any degree of certainty, then then your power measurement won't be very accurate. So that's how we display it. Now I would grab the reflected coupling and put that next to this, and that's what we would use to do that. So now I won't bother with that, but I will show you. Okay, so now remember that this is the coupling, so it's 60 dB down. Now if I want to look at what the influence of the incident signal is that's going into this load right now on the reflected port, we should see very little. And again, I got to move my reference up because it's below. Let's move this up to, let's go up to the top. And that is now the directivity, because what we're looking at is the energy that's leaking into this port from the forward direction. But notice it's down somewhere in the 80s, minus 80. So in other words, you would take 85 and you'd subtract that away from 60, and you get about 25 dB of directivity. These couplers don't exhibit the best directivity. The bidirectional type, which are the ones we use in our broadcast power monitors, are much better. They're 30 to 40 dB directivity. What that means is the resolution of your reflected power measurement, for example, because the reflected power is always going to be much lower than the forward power, at least we hope it is. You want to be able to resolve that to a very, very low level, so all you're seeing is reflected power. So again, remember I said 30 dB equates to about 1.06 to 1 VSWR. So most broadcast antennas, for example, the FM antennas that we used to use down in New York, that was the spec at the factory. What the actual right at the antenna input was about 1.06 to 1. Well, if your instrument, it can only measure a signal that's about 1.3 or 1.4 VSWR, you're never really going to see what it really is. Your instrumentation is introducing an error that doesn't actually allow you to see what the real signal is. So there you go. So that's why we do both measurements. The advantage of this style of coupler is it has compensation built into it. That's the whole deal on that. Okay, so let's do some other two-port stuff here. Let's take a look at this filter here, and then tell you what, Malcolm will look at one of your filters, and I'll see where we are. So for that, I need adapters. Now again, I'm using adapters here, so we're introducing a slight bit of error here. I'm going to put these BNC cables on, or adapters on this. So we're probably going to introduce my guess would be about 1/10 of a dB of error, in amplitude error. There's probably very little phase shift in these or anything, but well, it depends on what you're doing. If you're up in the microwave range, if you're measuring 27 gigahertz signals, well, then there's phase shift in this. Yeah, let's put these on first. Now I'm going to change the stimulus again. Well, let's start with where it is, and then we'll move it in. All right, so this is a bandpass filter that's adjustable between 406 meg and 512 meg. And this is really kind of cool because it lets you see what the actual response of this cavity is. Oh, look at that. Now, interesting. I've got this, pardon me, I've got this sweeping out to a gig, right? And this is a 450 filter. I have this tuned up right now, I believe, for the input frequency of the 448.725 machine, or at 443.725. And you see there's a sharp peak there. And you notice the roll-off is pretty steep. But look at what's going on. You've got a null up there at about 600 and something megahertz. So these are not infinite response filters necessarily. Now, if we really widen this out, we probably see harmonically related peaks from this filter. As a matter of fact, we could do that. Let's go back to our stimulus, and let's go crazy. No, that's not what I wanted to do. I wanted to go here, and I want to change this. Let's go up to 2 gig. Look at that. That's at about 1 point. And I think if you do the math on this, that's going to be harmonically related to this filter. So now let's zoom in on this. Let's get this down to something that's usable here. So let's go into 442, let's say. And let's go to, notice what's going on. Yeah, this is still, we're still up at, let's go to 445. And you see now we have a much broader, because we're scanning over, we're spanning over 442 to 445. So all of a sudden now that peak doesn't look like as sharp as it is, but it really is. I mean, but that's the bandwidth. But look, it's already down 3 dB at, if it's 725, let's put a marker in here. You can add markers, and there's 443 and a half. That's where you see the number 1. So let's grab this marker, and let's move it where I think the peak is, which is about there. 443.62218. Okay, so this filter was laying out in my car all night, and I can still feel that it's cool. So now you see the temperature effect of a filter. So this is why a network analyzer is indispensable in doing this kind of thing, because, whoop, look what I can do. And I can see what I'm doing. Look at how I'm moving that peak around, right? And I can get it precisely where I want it, I think. Well, what I would do here is I'd set the marker for what my desired frequency. Let's add another one. So let's set this one for, what did I say, 443.725. Okay, so that's my number 2 marker. So now if I want to tune this filter for precisely, oops, went too far. I keep going the wrong way. There we go. See how it happens with these filters. They're not, you could think you're going in the right direction, and the mechanical part of this is fighting you. So you gotta screw with this to get it, literally screw with it to get it where you want it. So that's close enough. And then the loss, as you can see, is about 1.7 dB. That's the passband loss. So filters are not perfect devices. Okay? So what else can we do? We could do an S11 measurement here, where we could look at the actual impedance and do lots of different things here. So, okay, so that's a filter. You want to try one of your filters, Malcolm? What? I'm sorry. What is?
SO239.
Right. I have adapters for that. That's. And oh, sure. Go ahead. And pick one. Tell me what what we think the bandwidth is, and
That's a 40-meter bandpass.
okay, so 7 meg to something.
Well, it should be 77.3, and it's designed to have maximum insertion loss on 20 meters.
Okay. All right. All right. So let's get this out of the way. So this is one we use on field day. This is a 40 meter. Is this? Do we know? Oh, it's a bandpass filter. Well, we'll find out if it's a bandpass filter. Now, technically, I should be recalibrating the instrument. Well, actually, no, that's not true. I have it calibrated for down to 1 meg, so we should be okay. So we'll put the port 2 on the output, and we'll put port 1, on the input. Got to be careful with these cables. When I say they're expensive, they're hundreds of dollars each, and the cal kits are even more. Okay, so this isn't going to tell us very much. Let's go down to about, let's say 6 megahertz. Oh, no. And you said maximum attenuation was on 20, so let's go up to about, let's say 15 megahertz. Gee, look at that. So at 7 megahertz, okay, and down at 15 megahertz, it's got about 70 dB of attenuation. Not bad. Now I can move the markers around here. I can put them where I want to put them, but why aren't they? Oh, okay. Well, but anyway, this is indeed a bandpass filter. But let's see how good the bandpass is down below. Let's go down to 1 megahertz. Look at that. That's pretty symmetrical. Looks good. So it's about 3 dB down, which would be somewhere about 1/3 down from the reference. You're at about 6 and change megahertz. I could go in there and put a marker, and we could measure it, but there's virtually no insertion loss on frequency. Let's go right on. Let's say let's do 7 megahertz. Let's put in a marker on 7 meg. I would expect that from anything that's in the HF band. You're going to have more attenuation with something like this because you're up at 450. Obviously, this is just the physics of how it all works. But that's a pretty good looking filter. Now, but let's also take a look. Let's keep going north here. Let's go up to 30 megahertz. And you notice the sweet spot is designed for about the 20 meter band. It's right around there, and about 14 megahertz. But you see what's beginning to happen? The response is beginning to rise again. Okay. I think if we kept going here, we might see. I don't know. We'll see what happens. Let's go to 100 megahertz. You see there's another peak there. It's still attenuated by about 25 dB, and it keeps going up. Why do we think that's happening? Capacitance, you got it. You hit the nail on the head there, man. Oops, what did I do? I made a mess. Let me go back down to what did I do? I hit the wrong. Wow, that's out now. We're out at this is, I'm up at 500 megahertz. So, obviously it's not designed to operate there. It's not designed to attenuate signals. But if you had lots of harmonics, filters are not necessarily infinite. They don't necessarily have a skirt it's in the area of interest that the skirts are, but the filter itself, as you can see, is not quite perfect everywhere, but then you wouldn't be using a filter like this at 500 megahertz. Okay, so I got one more thing I can show. I brought this mystery antenna. I'm not sure I'm going to be able to get connector on that. It's an N female, and I have real quick, and then I'll be done. And if you have any questions that I can't answer, I'll just say I'll get back to you on that. Let me use. This is the Nano VNA. I brought this one along. This has got end cables on it already. You know, it'd be interesting to see too, real quick. Just do this real quick. I got this from one of the Chinese manufacturers, and they gave us a cal kit. Let's see how good the cal kit is. At least the load is anyway. That's the short. There's the load. I'm just kind of curious while we're at this. And they gave me a barrel connector. Let's look at that first, just out of curiosity. And I promise I'm done. Unless you want me to do finger puppets, I can do that too. You really have to be adept at doing that if you can't get the HDMI cable to work. Oh, that's a real good load now. Well, signal's about 100 dB down. Okay, so I think that's a pretty decent load actually. Oh, wait a minute, I got to change the. I'm sorry, I got to change the. Got to go back to a 1:1 measurement. Oop, that's much worse. But that's not too bad. That's pretty respectable actually. It's about 40 dB return loss. That's not bad at all. Let's see how. Well, I got an idea. Let's do one more thing. Let's take one of my really expensive loads and see what they look like. All right, so this is the end female, so I don't need the barrel. And this is the load. So what are we seeing here? We're seeing about, I could actually copy this, do this tray. Oh, one thing I didn't show you, well, I'm going to do with the antenna is how you can generate a Smith chart. This one looks a little better. It's not a whole lot better, but it does look better, particularly at the, it's better than 40 dB everywhere. But even, you know, loads have, look at, there's a dip in the return loss, which means it's an improved return loss of, 65 dB at about 165 meg or something like that. So, they're not necessarily flat, but that's a pretty good quality load. 40 dB is about 1.03 to 1. 44 dB, it's 42 or whatever I have the marker set for. Okay, so one last thing we'll do here. Let me see if I can get this onto that antenna, and we can see what this mystery antenna is. Where am I? This is S11. I'm gonna go back to stimulus here, and I don't know what this was. Marked 2 meters, but I don't know about that. We'll find out. Now, of course, when you measure an antenna, especially a VHF antenna or UHF antenna, you don't want to do what I'm doing. It wants to be on a pole with no obstructions near it, because you can have reflections which will. Just putting my hand. Look what's happening. I can tune the antenna with my hand. So now that's return loss. Whoops! What happened? Looks like this is a 450 antenna, if I had to guess. There's the most pronounced. Well, no, I take that back. It might be. Well, it's probably a VHF antenna, because the dip is at. I don't know why that's. I'm probably not making a good connection here. That's why it's happening. But you see, there's a couple of pronounced dips here. One is about 15 dB. By the way, that's a typical return loss on a broadband antenna. About 15 dB. It's not great, but matter of fact, the antenna that we have up at the site for the VHF, for both repeaters, 15 dB. That's what the spec is. That's what the old Phelps Dodge spec was. Now, you notice there are resonances in other places. Well, probably harmonically related. Look at that. 140. Yeah, this looks like it's about 149 or 148 megahertz, but there's also another resonance point up in the 400, which is probably a third harmonic, right? 300, and yeah, it's not quite 450, but then that's not quite 150. So there you go. Now, again, you can see the influence of nearby objects and things like that on your antenna performance. And with that, I think I am done showing you toys and games here. Oh, one more thing. One more thing. Let's do one more thing. Let's look at a. So we've been looking at a log magnitude of these things, which are basically scale. Oh no! But what that's doing is again, remember, that's sweeping from 1 meg to 500 meg. That's just kind of useless. We don't want to do that. We think this is a VHF antenna. So let's go into about 146. Oh, and the picture's getting much better. And let's do 150. Oh, look at that. So you notice how I'm moving this around and it's changing it's actual. Whoa, look at that. Well, that's because my connection's bad here. But this antenna is inductive at 146, which means it's too long, right? You see that remember above the baseline in the middle is inductance. So this antenna is not terrible looking, but it's probably if we move this around, we'd find the sweet spot for it. But so what this Smith chart is actually showing here, and we can plot this, is it's showing us both the reactive component because it's above the baseline, and then if we grabbed hold of a circle here and brought it down to the bring it down to the impedance line, that would be the actual impedance. Okay, and there you go. So, and I'm getting tired of holding this, so I'm going to put it down. And there you go. So, anybody want to see what the rubber duck looks like? I can't get this off of here now. Uh-oh. I can't. Well, yeah, it's because I'm messing with the connector. Actually, we could do that too. One more thing. Let's do one more thing. I brought my my fine Anytone DMR radio with me, and I have the rubber duck. And I've never done this, so I don't know what this is going to do. Let's put this down. So this is actually an antenna. I paid $10 for that antenna at Hamfest. I don't know why, but I did. There you go. It did serve some intrinsic purpose. Oops, that's the wrong end of that. I don't want to do that. All right. There, let's go back to, well, no, let's do that. This is supposed to be a 2-meter 440 antenna, is it? Not really. But that's what it's supposed to be. That's typical of a rubber duck, by the way. It's, So let's go back to, I don't know, this. I might have damaged this antenna for all I know. I don't know. Let's go back to response. What are we doing? We are doing an S11 measurement, right? Okay, let's go back to log magnitude. I think this antenna is bad, to tell you the truth. Yeah. What's that? Could be, but you should be seeing something there. But it's, oh, you know what? I think I'm not making a good connection here. There we go. That's better. About 10 dB return loss. That's not terrible, but it's not, it'll get a signal out, but that's, okay. I don't know why that's, oh, you know what it is? This is a very deep connector. It just wasn't making connection. That's what the problem was. Okay, so that's all I know about vector network analyzers for today anyway. Any questions? Was this, thank you. So was this helpful in maybe clearing up some of the confusion about what to do with your nano VNA. By the way, the nano VNA is, I think these things are great. You know, as I said, I got this one. I have two. I have this one, and I have this one's got end connectors on it, and it's in a metal case. And you know what? For 125 bucks, you get a lot of stuff. I got a little carrying case for it. I got the two cables. I got, you know, a calibration kit, which is probably okay. Here's the difference between, really the difference between one of these and one of these. Dynamic range. You notice that this instrument has at least 100 dB dynamic range. That means that you can measure a signal down that far, minus 100. These, not so much. They're probably good for about maybe 70 dB, 60 to 70 dB. So for most things, like measuring return loss on an antenna, you know, sweeping an antenna that we would use in the HF spectrum, these are fine. But if you were going to tune up, let's say, a filter network for like a repeater or something like that, where you want to see nulls that are down 90 dB, you know, like you remember you have your pass reject filter network, and you want to see what the actual reject, where that, first of all, where the null is very precisely. And you notice how I had to mess around with the tuning on this to get it right exactly where it was supposed to be. You need 100 dB or better dynamic range. There are instruments that have even higher dynamic range than this one. I suspect that this is probably even more than 100 dB, but this is what you can display. There are instruments that do 150 dB, which is pretty standard in the wireless business these days. And again, this is what would be a lab grade instrument, but it's on the low end. There are more expensive ones that are made that do much more than this one. Only is, I think the limit on this is 4.5 gigahertz. They make instruments that go up into, you know, many gigahertz and have multi ports on them, more than 2 ports. You can have 4 ports, 8 ports. One of my customers is actually Rhoda and Schwarz in their broadcast division. They buy power meters from us, but they're in the test equipment business, and they make some really sophisticated network analyzers that are in the order of like $250,000 a piece. So you got to be doing some really, you know, precision work with those. If we make a power meter that's just like, I brought one of ours along here. This one, again, this one is a trade show. Oh boy, they really made a mess of this thing. This is a trade show demo. So this is a directional coupler. This is a bidirectional type directional coupler, and this is a 7/8 EIA. So this is 7/8 inch rigid cable this would be used with. And this one's been beat to hell because it was at a trade show. And so this box is what we make. We buy this from another manufacturer. We put this together. We calibrate the entire system by sweeping the directional coupler, which is what we did earlier. So we know what the coupler loss is, and then we actually calibrate the sensor. There are a pair of sensors in here. There's one for forward and one for reflected. So we can do measurements. Now, we're bringing out a meter pretty soon that can do vector analysis, actually. It can do simple VNA type of things. You can look at the impedance and whatnot, because we're able to measure not only the amplitude coming back, but the phase of the signal. So we make these with bigger lines. I mean, the biggest one we've ever put a line on was a 12-inch directional coupler, 12-inch in diameter. It was made for a non-broadcast application. It was made for something in industry, which I really can't say what it was for because we had an NDA that we had to sign. This is an experimental thing, but 2.5 gigawatts worth of RF power, and that's not effective radiated power. That's 2.5 megawatts of power that they needed to measure, and they put a pair of our meters on the same directional coupler. They made the line section had 2 directional couplers on it. They want to be able to compare the two to make sure they were within tolerance, and we met the spec, which was 1%. So there you go. All right. Any other questions? Anything? Okay, good. I'm done. I'm going to clean up, and I think there's another presenter, right? So hope I didn't run over here. So you want to check it? Oh, let's do that. Sure, let's do that before I shut everything down. Sorry, Lou. Yours is SO 239. Okay.
It's just a heads up that we have some Western County areas.
Right. We'll make this quick. Yeah. I'm sorry. I don't mean to be. You know. Okay. Okay. So Lou made this. This is a two-band Yagi, right? It's VHF
Correct.
and UHF, and then you made your own duplexer.
Right.
And
I have these schematic.
okay, so what we want to do is find my SO239 adapter. Now, understand that this is probably going to be impacted by the surroundings here, because this is a directional antenna. So we may try to aim it toward the window if we can, but let's get the stimulus set up here. So we think this is 2 meters and 440, eh? So let's start at about 140, and let's go to, let's say, 500 meg, and let's see what we got. Well, we have your resonant frequency looks like, well, and I gotta see if I can minimize the, there we go. We can get this minimized, but it looks like you got 2 resonance points, which you're a little high, Lou. You're about 162 on the VHF side, and maybe a little low. Well, I don't know, a little low on the. You're about 430, 438, something like that. So it is indeed a dual band system. Now, what you would probably want to do here is we would separate out the components and measure them individually to see where the issue is, because Lou's intention was to have this resonant in the 2 meter band, which would be 146 to 148, I would presume, somewhere in that neighborhood. So there's 2 sources of error here. Maybe the antenna's cut too short or too long, or maybe there's an error in here. The way you figure that out is, what we would do, again, this is a device under test, this box. So what you could do is you'd have to connectorize these 2 cables, and measure the box, see what the resonance of the, where the band passes of the. Now remember, we're looking at return loss. That's why it's dipping down. It's not. That's actually the. We could actually look at the band pass if we wanted to, which you're sort of looking at upside down. But so we could determine whether it's the antenna by connecting the antenna separately, or whether it's the box itself. Now remember too, with this type of an antenna, there's interaction between the 2 antennas themselves. But that's the proper way to do this. But and what was your, what did you find with this? That you had a high, you can see the dip there. It's at about I don't know, it's probably in the 170s, it looks to me. Yeah. And then,
I've made these Yagis before without any sort of
right.
duplexing circuit, and they're pretty accurate.
Oh, sure.
So
Yeah.
my suspicion is that if I were to rebuild the circuit, I would get.
And I got to tell you something. The way to probably fix this, you're going to think this is crazy, but your component values are probably okay. Did you wind your own coils for this? Yeah. Stretching the coils, and that's the first thing you want to start with, is doing that. You would take this apart and you would mess with it. Now, of course, as soon as you put the cover back on the box, it's going to change. So
work in progress.
Yeah. No.
8 years that I've
No. Listen, you got this far with it. No. Oh, wait a minute. This is how we learn how to do things. You got this far with it. He's got this close. This is not bad. So, this is what we would do in the lab. You do the same thing. You design it and it doesn't work where you want it to work, so you tweak it. This is what you have to do. Well, that's the part of RF engineering that's, kind of black magic. Some of it is, you can calculate, you can do all this stuff, and then when you go to build it, it doesn't work the way it is on paper. So no, I don't, I'd say it's a pretty good first shot. But of course, again, you really want to do this in free space. I don't want to be, in other words, I'm not influencing it too much because it's a directional antenna. If I point it toward me, or see it, oh, look what I'm doing. But I'm putting my hand on here. Okay, I'm tuning it with my hand. So look at that. But I'm knocking the antenna off of resonance by doing that. Well, or into resonance, as this case may be. But I'd say it's, it's for a first shot at this, Lou. It's not bad. I mean, you got to, it just needs, and you can do this with a nano VNA. You can do this. You could plot this like this, and play with it, tweak it until you get it right. But you want to put this up on a pole someplace. That's the problem. You want to get this thing away from, any influences, because you're getting reflections in this room, any metallic surface in here, or, even if I move it, you can see what's happening here. So I don't think that's bad at all. Okay. All right, now I'm really done.